QIQT 2023, the fourth day. Let me quickly introduce Dr. Mishra. So Dr. Devendra Mishra is an associate professor in the Department of Physics, Institute of Science at Banaras Hindu University, Varanasi. His research interest mainly is in the field of quantum optics, quantum information and quantum technology. And the title of his talk is Quantum Sensing and Imaging with Non-Classical Light. With this brief introduction, let me hand it over to Dr. Mishra. He has already shared your screen. Thank you. Please go ahead.
Thank you, Dr. Nirmalya. First of all, I will like to thank organizing committee of QIQT for inviting me to present my work. Let us celebrate we are celebrating the National Technology Day today. So happy National Technology Day to all of you. In the era of quantum technology, around the world, huge number of investments are being done by different countries. So we are interested in quantum technology, and our focus is in studying about the quantum sensing and imaging by using the non-classical light. In quantum sensing, we have a large number of areas. So our focus is to study the quantum sensing by using optical interferometry, that is using photons. Let us outline of my talk is we will introduce in brief about some notions of quantum optics. Further, we will discuss about some detection schemes, and then we will discuss about the classical and quantum parameter estimation by using Fisher information and Kramer-Rao bound. Further, we will discuss about our some basic results and summarize our results. A single mode pure state can be written in terms of ket psi, which is a superposition of Fock states in terms of this relation, and we can write annihilation operator and creation operator by using this relation. So annihilation operator operated on Fock state can be written in terms of square root of n minus 1, and annihilation operator operating on vacuum state gives us vacuum, and creation operator operating on Fock state gives us n plus 1 state, get n plus 1 state. Coherent state is an eigenstate of annihilation operator, and we can write the canonical position-like and momentum-like operators in terms of P and Q. There are a number of phase space distribution functions. The earliest one is Wigner function, which is a non-singular distribution of for all states, and it is known as quasi-probability distribution function. This is in contrast with classical phase space probability distribution function. And according to Hudson theorem, a pure quantum state is non-Gaussian if and only if its Wigner function has a negative value. Sorry, this is a non-classical. Okay. So another quasi-probability distribution function is P function, which is a diagonal representation of a state in coherent state basis, and we can write rho as integral of P alpha get alpha bra alpha d2 alpha. Further, we can discuss about the Gaussian Q function, which is a smoother version of Wigner and Glauber-Sudarshan P function, and it is equal to 1 upon pi bra alpha, and operated on this is the expectation value of observable O. Okay, so in general we can write the Wigner function, Q function, and P function in terms of T relation, and okay, so the properties of the properties of okay, the properties of Wigner, Husimi and P functions are can be assumed in terms of these relations. W alpha is equal to 1 upon pi W alpha 0, P alpha is 1 upon pi W alpha 1, and Q alpha is 1 upon pi W alpha minus 1. So these three distribution functions are related to operator ordering. So Wigner function is associated with symmetric ordering of operators, and Glauber-Sudarshan P function is associated with normal ordering of operators, and Husimi-Kano Q function is associated with anti-normal ordering of operators. Gaussian states and processes in phase space can be seen as circles or normalized Gaussian probability distributions. Coherent state can be viewed from the top, and ellipse represents a Gaussian probability distribution function. So the vertical blue line and horizontal green line correspond to position and momentum eigenstates respectively. We can define displacement operator in terms of the operator e power alpha a dagger minus alpha star a, and squeezing operator can be defined in terms of e power half psi a square minus psi star a dagger square. So in phase space, we can see that this circle can depict the vacuum state, and if we squeeze this vacuum state, we can have squeezed vacuum state. Further, if we displace the vacuum state in phase space, then we have coherent state, and further, if we operate on this this coherent state squeezing operator, we can have the squeezed coherent state. So in this way, we can find out different quantum states. Let us describe in brief about the quantum nature of beam splitter. Classically, we can describe the beam splitter which have one input and two output. Okay, if we don't care about the other input, so this is right in classical version. But in if we go in quantum case, so the unused port also plays. So if we leave the unused port, then our analysis will be wrong. So in general, the quantum optical beam splitter can be described by input-output mode operators. If A1 and A2 are inputs of the beam splitter, and A3 and A4 are outputs of the beam splitter, then output mode operators can be found out by using this relation. Okay, using the beam splitter, we can construct linear interferometers. Passive linear transformation, that is following SU2 group formalism over M mods, are defined as the unitary transformation U, which act unitarily on the creation operators of the mods A1 dagger, A2 dagger up to AM dagger, as well as on the annihilation operators A1, A2, AM using this relation. So we can find out the linear interferometer transformations by using the unitary transformation, unitary operator U with this relation. Okay. So by using the beam splitter formalism, we can construct the Mach-Zehnder interferometer. Here, we can see that this Mach-Zehnder interferometer consists of two beam splitters described by the beam splitter operator, unitary operator B and B. And we can use two inputs, that is known as probe preparation. And after that, after transmission from the first beam splitter, we have A and B. Inside the interferometer, we can see the modifications in the signal by using the phases phi A and phi B in both arms of the interferometer. And these two signals mixed up by the second beam splitter, and at output we have the output signal which we can measure to know the information about the modifications inside the interferometer. So in general, Mach-Zehnder interferometer can be divided into three steps. First step is probe preparation, second step is probe modification, and third and crucial step is probe readout. Using Mach-Zehnder interferometer, we can know about the phases, maybe phi 1 and phi 2 in both arms, or in any one of the arm of the Mach-Zehnder interferometer. Okay. So our task is to know about the phi 1 and phi 2 by using the Mach-Zehnder interferometer, by using non-classical light and quantum measurements. Suppose we have observable in measurement scheme, we have observable O dependent on the phi, which we are trying to know about that. So the average of observable O phi is in terms of get psi. By using the state get psi, we can know the expectation value of observable O phi. Suppose we have a slight change in phase, that is delta phi, then the expectation value of O using phi and delta phi can be written in terms of this relation. So we can use the error analysis to know about the error in knowing about the phase phi by using this relation delta square O divided by absolute value square of delta rate of change of expectation value of observable O with phase, unknown phase. This is the ratio of the signal noise to how the signal changes with respect to phi. By using the Fisher information, we can determine the theoretical lower bound to the error delta square phi. And in case of pure state, we can find out the Fisher information in terms of this relation, and the error in unknown phase phi is bounded by 1 upon f, which is known as the quantum Kramer-Rao bound. Why it is quantum Kramer-Rao bound? We are using here quantum resources, so we call it as quantum Kramer-Rao bound. And why quantum Fisher information? We are using here quantum states, so we call it quantum Fisher information. There are many problems in computing QFI, quantum Fisher information, for mixed states, which is computationally difficult. And proposed methods of estimating the QFI have scaling that precludes their implementation on near-term quantum devices. Okay. The giants behind the quantum Fisher information and quantum Kramer-Rao bound are Harold Kramer, C.R. Rao, and Sir Ronald Agelmar Fisher. Okay, so these works have been done around 1945 by three giants. Estimating phi, unknown phase phi, from the measurement signal can be done by using this relation N, B, F, and NAF, where AF and BF are the mode operators of output of the Mach-Zehnder interferometer. So, okay, task is to minimize this error. So how we can minimize this error? In knowing about the unknown phase, earlier work showed that using coherent state and vacuum as the inputs of Mach-Zehnder interferometer, we can find out the error in estimating the unknown phase phi is equal to 1 upon square root of n, where n is the number of quanta used for the measurement. So if you see this relation delta phi SNL equal to 1 upon square root of n. So we can see that the sensitivity of the interferometer can be improved enormously by using this number of quanta, that is energy using in input of the Mach-Zehnder interferometer. But this may not be an option in biological measurements. Biological measurements are in the extremely high precision measurements. Better sensitivity for the same value of n could be achieved using non-classical resources and measurement schemes. The first practical scheme of the short noise interferometer, which uses Gaussian squeezed states, was proposed by C.M. Caves, and further using this we can reach up to the Heisenberg limit, that is, we can enhance the sensitivity of our interferometer. By using this concept, we have detected LIGO experiment detected successfully the gravitational wave. Okay, so in squeezing assisted interferometers, this regime limits the range of phases where the high sensitivity is provided, while the optical power limitation could be not so significant in smaller scale, that is tabletop interferometers. Question is, which state is optimal for the best sensitivity of Mach-Zehnder interferometer? Dowling showed that the known state, which is the superposition, which is a superposition of two mode states, get n0 and 0n. Using this, we can enhance the sensitivity and attain the Heisenberg limit using the Mach-Zehnder interferometry. So, known state protocol is often referred to as super sensitive and super resolving. So, what is the problem? Problem is in generating the known state having large number of photons. Okay, so for large energy, problem is in generating the known state. So our task is to search about the alternative non-classical states and measurement schemes to enhance the sensitivity of Mach-Zehnder interferometer. We studied about the enhancing sensitivity of Mach-Zehnder interferometer by using squeezing assisted interferometers and two-channel detection scheme. Here we used SU2 interferometer and we investigated the possibility to broaden the phase range of sub-short noise sensitivity, and we showed that this goal can be achieved by implementing detection in both output ports with optimal combination of the detector outputs. Okay, this is our model in which we use DOPA, that is generating the squeeze light. After this, these two signals are injected via the beam splitter 1, and inside further the signals B1, B2 travel inside the interferometer, and after passing through the second beam splitter, we are again using the two squeezers by using DOPA 2 and DOPA 3 at the output in measurement stage to cop up the loss inside and outside the Mach-Zehnder interferometer. Loss inside the Mach-Zehnder interferometer and output of the Mach-Zehnder interferometer can be mimicked by using a fictitious beam splitter which have one input and okay, so we can assume the perfect approximately 99% transmission rate of the beam splitter. So we can see here, this is the beam splitter, fictitious beam splitter having transmittivity mu and having transmittivity mu. These are the M1 and M2. Inside the inside the interferometer. So these two beam splitters mimic the loss inside the interferometer on the two arms. And at the measurement stage, at outputs of the Mach-Zehnder interferometer, we are studying, we are putting the fictitious, we are considering the fictitious beam splitters by these two beam splitters, which mimic the losses at measurement stage of our task. Okay. So there are different measurements limit. First one is quantum projection noise limit, which we are not considering here. The main is short noise limit. Using in photo detection, power of incident light is P equal to IA, where I is intensity of radiation and A is area of the detector. So photo detector converts the optical signal into current signal I0, which is G E eta P equal to P upon S slash omega L, with gain G and quantum efficiency eta. The noise in photo detector fluctuates the current around I0, that is IT equal to I0 plus delta IT, with delta average value of delta IT equal to 0. The RMS noise current consists of two main parts: the short noise given by Schottky formula and thermal noise. So this is the limit which we have discussed earlier, and using quantum resources we can consider the quantum noise limit, while the short noise limit defines the best possible sensitivity in a perfect setup, that is eta equal to 1. The quantum noise limit gives the achievable sensitivity for given experiment with total quantum efficiency eta total along the optical path using detector efficiency. And the ultimate limit is Heisenberg limit. These are different kind of some measurement techniques. Here we can discuss about the single mode measurement. This is homodyne detection setup. In homodyne detection of state rho, the dashed red line represents the beam splitter. Balanced beam splitter means 50-50 beam splitter, and yellow describes the local oscillator. That is, we are using here a strong coherent light. The blue circles are photodiode detectors. Changing the phase phi inside the local oscillator allows one to measure the rotated quadratures. Okay. The balanced homodyne detector corresponds to a joint noisy measurement quadratures of quadratures Q and P. This is a Gaussian measurement which yields two real outcomes corresponding to the real and imaginary parts of alpha. The POVM elements for balanced heterodyne detection scheme can be written in terms of pi alpha, and unbalanced heterodyne detection scheme can be described in terms of this pictorial arrangement. We can also consider any Gaussian, non-Gaussian measurements. Any Gaussian measurements can be implemented by Gaussian unitary operators and heterodyne detection scheme, since it can be implemented by Gaussian unitary operations and homodyne detection only. So there are three kinds of non-Gaussian measurements. First one is single photon threshold detection. That can be described in terms of POVM elements. By these two POVM elements, this binary measurement only distinguishes the vacuum state from other states. Other one is, which is more important, that is parity detection, whose POVM elements can be written in terms of these two relations. This is a binary measurement of the parity operator, which is -1 raised to a dagger a, yielding, as its name indicates, the parity of number of photons of the measured state. Third one is photon number resolving detection, whose POVM elements are the pi m. Okay, the projections onto Fock states. Okay, we here discuss about the alternate two-channel detection scheme, which is a generalized version of direct detection scheme. In this scheme, we consider the optimal combination of two output signals, that is N1 and N2. So we discuss about the observable O equal to K plus 1 N1 and K minus 1 N2. That is, using this, using this observable Nk, we can find out the error in estimating phase phi. So delta phi square is equal to expectation value square of expectation value of delta Nk divided by square of rate of change of n minus phi with phase phi. So the value of k that minimizes this value provides also the best phase sensitivity. Optimal value of k and corresponding value of delta phi are k optimal is cos phi and delta phi is delta phi minimum. This optimal strategy gives us a completely flat value of delta phi. At the same time, it creates a vicious circle. We can see here vicious circle. The factor k depends on phi. Therefore, consider the suboptimal strategy by using k suboptimal equal to cos phi a priori, where phi a priori is a priori mean of phi. In this case, delta phi square is equal to delta phi minimum square plus k square of cos phi minus cos phi a priori divided by sine square phi. So, in order to obtain the good phase sensitivity, we can have delta phi a priori much less than 1. Therefore, modest a priori knowledge of phi corresponding to delta phi a priori is independent of n and therefore could be much larger than, for example, delta phi SNL. It allows us to obtain a sensitivity close to optimal delta phi equal to delta phi minimum for all values of phi. So we can see here for single detector, we can see here the specific region where we can obtain the better sensitivity. And for the case of differential detection scheme, again, we can have some reason, specific reason where we can have we can find out the better phase sensitivity. But in case of our suggested proposed optimal combination of detection scheme, we can see that here a broad range of values of phi where we can find out the best phase sensitivity. So we can broaden the sensitivity of our interferometer, which is okay. So we can broaden the sensitivity of our interferometer. In this way, while the first two strategies, that is single detection and differential detection scheme, limit the range of phases where high sensitivity could be achieved, the third, which we have proposed here, allows to beat the short noise limit by the same amount for all values of phi, assuming some modest a priori information about phi. In particular, this information could be acquired using a preliminary low precision ranging measurement with broadened range of high phase sensitivity. Squeezing assisted interferometers can improve the performance of many techniques where they have not been used so far. So, for example, we can use our analysis to enhance the sensitivity of Fourier transform, infrared spectroscopy, and in aerodynamics also, where we can use the this technique to for environmental gas sensing. Okay. Our next study is to enhance the sensitivity of Mach-Zehnder interferometer by using Schrodinger's cat-like state, superposition of Schrodinger cat-like state and Fock state as inputs using two-channel detection scheme. Here, we inject the coherent state at one of the input port of the Mach-Zehnder interferometer, and our superposition of Schrodinger cat with Fock state, which is get psi, at another input of the Mach-Zehnder interferometer. And we study by using the two-channel detection scheme about the possibility of enhancement of sensitivity of our interferometer. This is our state, which is superposition of Schrodinger cat state with Fock state, and we are using quantum Kramer-Rao bound and quantum Fisher information. We can see here the variation of phase sensitivity shown in color bar with mod A and theta A. For approximately 1 of mod A, we get better phase sensitivity, which is maximum phase sensitivity is shown in the dark blue. For theta equal to 3 pi by 4. Okay. So further we can see the variation of delta phi phase sensitivity with phi. We can see here the combination of coherent, well-known combination of coherent and squeezed vacuum for single intensity detection, coherent plus squeezed vacuum using intensity difference detection scheme, and coherent plus squeezed vacuum using two-channel detection scheme, and vacuum plus superposition of Schrodinger cat state with Fock state, that is abbreviated as SCFS, and coherent plus SCFS. We can see here the better phase sensitivity in our case, that is combination of coherent and SCFS under some conditions. Again, we can see the variation of delta phi square with phi, for which we can see the phase sensitivity beats the short noise limit. Color bar shows the ratio of delta phi with short noise limit. These are the effect of increasing the number of photons in Fock state and variation of phase sensitivity in the Mach-Zehnder interferometer. The problem is in generating the superposition of Schrodinger cat state with Fock state. We have proposed a scheme for the generation of superposition of Schrodinger cat state with vacuum state, that is abbreviated with by SCVS. A schematic diagram is for the generation of SCVS. Here BS1 and BS2 are the beam splitters, CKM1 and CKM2 are the cross-curve media, and D minus I alpha describes the displacement operator, PS is phase shifter, and VNM is the von Neumann measurement scheme. So if we inject single photon at BS1 and we discard the signal D, the signal C is injected on second beam splitter BS2, and output of the signal output of the second beam splitter BS2, which is G and F. So if we inject F on cross curve media 1, and if we inject G on second cross curve media medium CKM2, the output of first cross curve medium CKM1, which is I, both are injected on CKM2. Output of one of the output of CKM2 is displaced by using displacement operator d minus I alpha, the output of this displacement operator, which is being injected on the phase shifter PS, output of phase shifter is used for the von Neumann measurement on the modes JLD. So using this scheme, we can find out the output which is in a series state. We can generalize this scheme for finding out the CFS state. Our next scheme is to enhance the phase sensitivity of Mach-Zehnder interferometer is by using the squeezed curve state, which is an alternative scheme as compared to our well-known schemes, that is coherent and squeezed vacuum and other studies. So here we use squeezed curve state as one of the input of Mach-Zehnder interferometer. Squeezed curve state can be defined in terms of if we use the curve medium described in terms of evolution operator UK gamma, where gamma is equal to chi3 L upon V, where L is the length of curve medium and V is speed of light inside that medium, and chi3 is susceptibility tensor of the curve medium. Okay, if we inject the coherent light beam on that curve medium, then we can have the curve coherent light beam, which is UK gamma get beta. Further, if we inject this radiation onto the squeezed medium, squeezer, then we have squeezed curve state. Squeezed curve state can be seen as a generalized state from which we can find out the coherent state if we assume xi equal to 0, gamma equal to 0, and beta is non-zero. Curve state can be seen as if xi equal to 0, gamma is non-zero, and beta is non-zero. We can find out from squeezed curve state the squeezed coherent state if we have xi is non-zero, gamma is 0, and beta is non-zero. Further, we can generate squeezed coherent state, squeezed vacuum state by assuming xi equal to non-zero, gamma is 0, and beta is equal to 0. And we can also find out the vacuum state if we have xi equal to 0, gamma equal to 0, and beta equal to 0. In this way, this state can be seen as a generalized state for non-classical resource as one of the input of Mach-Zehnder interferometer. We studied by using the combination of vacuum state and squeezed curve state. Using homodyne detection and single intensity detection and intensity difference detection schemes, we can see here the sensitivity of Mach-Zehnder interferometer with this combination. Further, we can see the we investigated about the combination coherent and squeezed curve state as inputs of Mach-Zehnder interferometer, and in this case we find out many situations where we can see the better phase sensitivity as compared to that of the combination of well-known states coherent and squeezed vacuum or squeezed coherent states. Okay, the schematic is same as discussed in our previous study. Here we are injecting the squeezed coherent state and coherent state at inputs of the Mach-Zehnder interferometer, and we consider losses inside the interferometer and losses at measurement stage, and we can see here the better phase sensitivity in our combination of inputs. We can see here comparison of coherent state with squeezed vacuum and coherent state and squeezed curve state, and we can see many instances where coherent state and squeezed curve state may give better phase sensitivities as compared to coherent state and squeezed vacuum state. This work is under review. So in conclusion, we studied the phase sensitivity in Mach-Zehnder interferometer with the squeezed Kerr and coherent state as the inputs. We discussed the lower bound in phase sensitivity using quantum Fisher information and quantum Kramer-Rao bound with the help of single intensity detection, intensity difference detection, and homodyne detection schemes. We find out our scheme gives better phase sensitivity in both the lossless as well as in lossy conditions as compared to the combination of well-known results of inputs as coherent and vacuum, coherent plus squeezed vacuum and double coherent states as input. Okay. So another works which we are here doing are the first one is based on phase supersensitivity based on SU11 interferometry, and second one is weak measurement and sensing. Third one is quantum LIDAR. So in SU2 type of interferometer, we have seen that we use the beam splitters, which are passive elements, passive optical elements. If we replace the passive optical elements, that is beam splitters, from the active optical elements, so here we can see we can use the active optical elements in place of beam splitters at the input as well as output stage. So we can okay, so the non-classical resource, if we use here classical lights at inputs, then inside the interferometer we are generating the non-classical light. So difference from SU2 type of interferometer is that in case of SU11 interferometer, we are generating non-classical light inside the interferometer stage, that is probe preparation stage. Okay, and at output stage, that is measurement stage, also we are using the active optical element. In this case, we using these two active optical elements, we are avoiding the optical losses. This scheme has been demonstrated to be able to reach the Heisenberg limit. So using this scheme, we are planning to study about the enhancement of phase sensitivity of Mach-Zehnder interferometer, and using our analysis, we are trying to study about the enhancement of sensitivity of different spectroscopic devices, for example of cars, coherent anti-Stokes Raman scattering technique. For example, another work which we are doing here, which is in a development stage, is weak measurement and its use in quantum sensing. Different ideas emerged on using weak measurements or weak values inspired methods in interferometry. Weak value measurement was introduced in 1988 by Aronoff, Albert, and Badman, and weak value of an observable can be defined in terms of the expectation value of weak expectation value of an observable A, which is defined in terms of the average value of A with pre-selected and post-selected quantum states, where ket psi f is post-selected quantum state and ket psi I is pre-selected state. When considering von-Neumann coupling between the observable A and a pointer observable P according to unitary transformation U equal to exponential of minus Ig A tensorial product of P in the weak interaction regime, the evolution of this system can be seen in terms of this relation. Thus, weak values are measurable quantities and can provide and amplification in measuring a small parameter, that is a phase, which can be significantly used in presence of technical noise. We are planning here to use this concept in increasing the phase sensitivity of our interferometer by exploiting the non-linearity of single photon. Another thing which we are studying here are based on quantum imaging. We are focused here on quantum lidar, which can be used in remote sensing at the ultimate limit. This study is being done in collaboration with M.K. Mishra from SAC Ahmedabad. Here, the concept of quantum lidar for using remote sensing at the ultimate limit was coined by Jonathan Dowling in a report which was published by Louisiana State University in 2009. Here we can see we have a target and we can send the signal and we can sense about the target by using the detection which is being used by which is exploiting the non-classical light beam. And using this we are trying to study the enhancement of phase sensitivity of our lidar system. So okay, these are my students which are engaged in these studies, and I would like to thank my collaborators M.V. Chokhawa and Farid Khalili, in addition with M.K. Mishra for these studies, and thank you all of you for your kind attention.
Thanks, Dr. Mishra, for a really nice talk. The session is now open for questions. Any questions? You may please unmute yourself and ask.
I have a question, sir.
Yeah, please.
Sir, thank you for the talk, sir. Sir, I have a doubt why these different schemes are giving different phase sensitivities. Like, yeah, we are observing that this, say, for example, coherent plus Schrodinger cat Fox states are better than coherent plus squeeze vacuum state. Yeah. The phase sensitivity when we calculate. So, but why is this the reason? Like, why do you think?
Basically, we are using the non-classicality of light beam at inputs of Mach-Zehnder interferometer to enhance the sensitivity. And different states have different non-classical features. So, if we consider the squeezed vacuum, it is showing the non-classicality of light beam in some context. And if we see the superposition of Schrodinger cat state with Fock state, it may show different non-classicality, which may be stronger as compared to squeezed vacuum. So this is the reason. In another way, we can say that the exploitation of non-classicality may show different sensitivity in different cases of non-classical states. Okay. In case of, as we have seen, in case of squeezed Kerr state, that is a generalized version of squeezed vacuum. We are using here Kerr nonlinearity and squeezing in addition as compared to that of squeezed vacuum, where we are using only squeezing. Okay.
Yeah. Okay, sir. So, like different.
I have a question. Can I ask? So, this is to ask you about in quantum imaging and other things. There are two things as far as continuous variable states are concerned. One is non-classicality and other one is entanglement.
Yes.
So there is a kind of no trade-off, but competition.
Yes.
As to decide which is resourceful.
Yes.
So
these non-classical
according to you, if you can say, yeah.
these non-classical resources are helpful in enhancing different kinds of sensitivity. So here we are focused only on the non-classical key of light beam, not the entanglement of light.
Okay, thank you.
Thank you very much.
Any other questions?
I have a question, Nemalya.
Yeah, please.
See, Devendra, excellent talk. See, my question is, typically angle variable, we face problem while measuring in quantum mechanics, the uncertainty. I was surprised to see that you did not face any problem here.
Sorry?
Angle variable, delta phi in quantum mechanics is a bit well-defined. And you did not face any problem here. See, whenever you have a compact variable like angle variable, finding uncertainty in quantum mechanics is a bit of a problem, unlike delta x, delta p. So you do not face any problem formally here?
I am not hearing properly.
Angle variable. I'm talking about angle variable. Measuring uncertainty in angle.
Okay.
Quantum mechanical is a bit of a problem.
So
here you have no problem. No?
This is not an angle. This is the phi is unknown phase inside the interferometer which we are facing, and we are trying to know about that unknown phase. That phase may be gravitational wave or other samples also. So any disturbance inside that interferometer, we are trying to learn about that.
Yeah, please comment.
I may have a comment here. What Professor Prashant Panigrahi is asking is the phase. When you write as a quantum operator, there is an issue. Like, as we know, how to define a Hermitian phase operator. But in estimation theory, we are not taking that. In estimation theory, it's a statistical variable. That's all. So we are not thinking with the quantum operator issue.
Yes. We are not considering here quantum operator. That is Beck, Parnett, and other.
Like what you do when you use the operators in non-classical lights, like for example, squeeze states, etc.
Yeah. Okay, thank you. Yeah.
Thank you.
Okay, thank you. So if there is no further question, let's again thank Dr. Mishra, and thank you for joining and